Hello, everybody. So far we have discussed finite state machines that have constant amount of memory, computations with constant amount of memory, and we discussed it from various perspectives. So we defined finite state automata, deterministic finite state automata, DFAs. We defined the language that they recognize as regular languages. We studied regular languages through closure properties and showed that regular languages satisfy interesting closure properties. And on the way, we also introduced non-determinism in this context and showed that non-deterministic finite automata are equivalent to deterministic finite automata. They accept the same languages. And we also showed that closure properties characterize regular languages through this notion of regular expressions. Furthermore, we showed ways in which to argue that some languages are not regular. So showed the limitation of DFAs through the pumping lemma and the Mile-Nerod theorem. And these limitations can also be used to show very powerful things, like the result about minimizing DFAs, which was very, very powerful. And we also discussed learning DFAs. Today we're going to introduce another notion, streaming algorithms. And in a sense, this is one of the highlights of this chapter in the sense that it is a very modern and important area of research. It's not new, but it is still very active and highly motivated. And we'll see how the things that we've done so far can help us say meaningful things about streaming algorithms. So all the tools we accumulated are already very useful to say meaningful things about something we really care about, like streaming algorithms. So when you think about streaming algorithms, consider the case where we have some stream of data. You can think Internet of Things. Think about some sensor that is telling us the temperature in a constant stream at every given moment, or humidity in the ground, or chemicals in a pool. And this stream is endless, and you keep on getting it. You cannot store it and then run calculations. Even efficient calculations like linear time algorithms become inefficient when you think about a very long stream. So essentially what you want is an algorithm that sees a bit, processes it in some way, and continues. From there on, it cannot see the bit that you've seen before. So you get one bit at a time or one symbol at a time, and that's it. You need to do whatever you want with it, but then it disappears. So this is the read once access, which is very similar to what we have with DFAs. As you can see, this memory of this machine is limited. It is a small memory. It can grow a little bit. It's not constant, but it is also not large. It's not linear for sure. Ideally, we want to think about the memory of this algorithm as being logarithmic in the length of the sequence, or perhaps polylogarithmic, but not much more. So you keep on seeing symbols in the stream, keep on processing them, and at some point the stream ends and you need to output an outcome. For example, perhaps the median temperature or something else. So at any given point, you need to be able to stop and output something that's relevant to the stream you saw so far. It's related to DFAs, it's not exactly the same. I also want to stay in this description very vague on the computation cost. So this machine gets bits and does some calculation at every stage, And we want to think about this calculation as being efficient, but we won't get into the details exactly. This won't limit the generality of what we show because all the algorithms that we will discuss have very simple computation. So the computation that this machine does at every given point are going to be simple. And whenever we show impossibility, it will be even stronger because it will apply regardless of the computational power of this machine. Why didn't we care about this in DFAs? Well, in DFAs, we had constant memory. So the computation at every point was a constant size computation that you could completely store, for example, as a lookup table. And therefore, we didn't really care. So given that we are in one state and we see one symbol, we can look at the table and then it will tell us what state to get to. But here, since we have more memory, this could be relevant. Let's give a simple example. The example is the language of all strings that have more ones than zeros. So now the string is binary. And all we want to ask is whether we've seen more ones than zeros or vice versa. What is a good algorithm for that? Well, one algorithm is just to store a counter that counts how many ones and a counter that counts how many zeros we've seen. And at the end, compare. Did we see more ones than zeros or more zeros than ones? That's a pretty good algorithm, but we'll try to optimize it a little bit further. And instead of 2 log n bits, we'll have an algorithm that uses log n plus 1 bits. And I'll tell you later why am I insisting on this optimization. So here is the algorithm. The algorithm will have a bit of memory, and will maintain a bit of memory B, which will always be the majority bit. Did we see more ones than zeros or more zeros than ones? And it will also maintain the difference. Instead of maintaining a counter for ones and a counter for zeros, we'll just maintain a counter that tells us how many more ones we've seen than zeros or how many more zeros we've seen than ones. Depending on what B is, that's how we're going to interpret it. Here's the algorithm in pseudocode. To initialize it, we'll initialize the difference to be 0, because till now we haven't seen nothing, so we've seen the same number of zeros and ones. And the majority bit doesn't matter. We can call it 0 or 1. We'll call it 0. But it doesn't matter because C already tells us that there is no majority bit. Now, whenever we see another symbol, we're going to perform the following algorithm. If C is 0, meaning that so far we've seen the same number of zeros and ones, then the next bit is going to be the majority bit. So we set B to be sigma, and we set C to be 1, because now we've seen sigma one more time than we've seen sigma naught. If C is not 0, then now we have two cases. Either B equals sigma, so sigma is the majority bit, and we need to increment C by 1, because now the difference between B and between B and not B has increased, or it is not 0. Sorry, or the majority bit is not sigma, and in this case we need to decrease the difference C by 1, because now we've seen one more minority bit, so the difference has shrunk by 1. When the stream stops, we can see if C is larger than 0, meaning that one bit appeared more than the other. And if the majority bit is 1, we know that we've seen more ones than zeros, and we accept. Otherwise, it could be that that the number of zeros was the same as the number of ones, or perhaps we've seen more zeros than ones. In either case, we need to reject. So that's the algorithm. It's a simple algorithm, and you'll see why there are going to be two reasons for which I'm chosen to be that pedantic and save on the memory. In any case, all you need to memorize is 1 bit, which is 1, and for C, you need log n bits at most. Because if you see a string that is all zeros or all ones, then the size of the counter will grow to log n. So now that we've seen an example, let's discuss in what way streaming algorithms are different than DFAs. For one, they can output more than 1 bit. So the algorithm that we just seen, we just wanted to know if there are more ones than zeros. But the algorithm could also tell us how many more ones than zeros they are. In particular, the specific algorithm we've seen has this information. Another point is that the memory or the space that the streaming algorithm can use can slowly grow. And so it is not constant. In particular, this means that we can recognize non-regular languages. And in fact, the language that we've just seen in the previous example is not regular. So asking whether the number of ones is larger than the number of zeros, this is not regular, and I encourage you to prove it in whichever way you want. It's not hard. And finally, sometimes you have variations on streaming algorithms. For example, when you're allowed to make a few passes on the data rather than one. So you would think about a huge amount of data that you don't want to access in a random fashion, but perhaps you allow yourself to go over it in a particular order, and you can do it once or twice or a few times, but not more. So this is less relevant to some of the applications I discussed before, the applications to Internet of Things, but there could be cases in which it is interesting. What is definitely relevant and important is that these algorithms can be randomized, and this will be important, and we'll see an example at the end of this video. So we've seen that DFAs and streaming are different, but if they were very different, then we would not talk about streaming right now. So now let's discuss the relation between DFAs and streaming in both directions. In one direction, it is kind of obvious. A DFA is kind of a streaming algorithm. It's even more restricted than streaming algorithms. So here is a theorem. Suppose that a language L can be recognized by a DFA M that has at most 2 to the p states, then L is computable by a streaming algorithm that uses at most p bits of space. So think for a second, how can we do that? And in general, all of these things that show that one model can capture another are usually operate via a reduction, via simulation. So the streaming algorithm can simulate the DFA. Proof idea, we define the algorithm A that initialize its memory to be the start state of M. And then whenever a symbol is read, it's going to use the transition function of M to update its memory. So at every given, so the memory of this machine always captures a state of M. And since there are 2 to the p states, you only need the p bits of space. And you're updating the state that the DFA would have been at every given point. When the string ends, you're going to output except if M is in a state which is final, which is accepting. Essentially, you're going to do whatever M would have done. So you're simulating M. Again, this part is not very surprising because streamings are just more powerful than DFA. But let's see the other direction. So the other direction is definitely not correct. We said that streaming algorithms can recognize regular languages. But if you think about streaming algorithms for strings that are bounded in length, then their memory is also going to be bounded. And therefore, we could build a DFA that agrees with the streaming algorithm, at least for strings, for inputs that are not too long. So to formalize it, let's look at the language L and define Ln, which is all the strings, all the words X in L that are of length exactly n. And similarly, L smaller equal n is all the words in L that are of length at most n. And the theorem is that suppose L is computable by a streaming algorithm using f of n bits of space. So the amount of space is f of n in relation to the length of the stream. So if the stream is of length at most n, then the amount of space you use is f of n. And if that is the case, then for all n, there is a DFA m with 2 to the f of n states, such that the language that DFA recognizes agrees with L on every string that is of length at most n. For longer strings, the DFA has no chance of simulating the streaming algorithm because at some point it will run out of states. But up to n, the simulation is going to be good. So to prove this theorem, we need to show how the DFA can simulate the streaming algorithm for strings of length at most n. And that's not going to be difficult either. So the states of the machine, M is going to be all the memory configurations of A. And since A uses f of n bits of memory, there are at most 2 to the f of n configurations of A's memory, as long as its input is of length up to n. The start state of M is just the initial memory configuration of A, and the transition is going to mimic what A does. So given that this is the memory configuration, this is the previous state captures the memory configuration of A, and now we read sigma, we know what is going to be the next memory configuration of the streaming algorithm, and this is the state we are moving to. So essentially here the DFA is mimicking, is simulating the streaming algorithm. Eventually we're going to accept every state that correspond to a memory configuration of A that would make A accept. A accept is a function of what is in its memory. And these are the states that M is going to accept as well. So let's give an example, and the example will be exactly the same language. And this is the streaming algorithm that we had before. And indeed, the reason that we optimized the streaming algorithm was because now that we're going to build a DFA out of it, and the number of states of the DFA are exponential in the memory, every bit we save allows us to build a DFA for a larger setting of n. Still, to fit it in the slide, we'll have n be 2. So we want a DFA that agrees with L on all strings of length at most 2. And this is the DFA. The initial setup of memory of the algorithm A sets B to be 0 and C to be 0. If you see 1, you move to B equals 1 and C equals 1, because now we've seen one more 1 than 0. If we see another 1, then we move to 1, 2, because now we've seen 2 more 1s than 0s. If now we see a 0, we actually move back to 1, 1 because the difference has shrunk. And if we see 0 here, we move to 1, 0 because now there is no difference. In this state, we've seen both zeros and ones the same number of times. If you notice, all the way from this root to this depth 2 nodes, what we're doing mimics the algorithm A. Some of the things we do for this level are also mimicking the algorithm A, but some do not. So for example, if we see the stream 1, 1, and 1, we think that we've seen 1 twice more than we see 0, and this is not accurate. That's fine because we are not guaranteeing anything for strings that are larger than n. So here, for strings with more than 2 bits. But up to 2 bits, we're doing exactly the same thing. And you can see that the except state are those where we saw ones more than we saw zeros. So that's the reduction. And let's ask ourselves, so this is the only streaming algorithm that we've seen so far. We've seen an algorithm, this algorithm that uses log n plus 1 bits of memory. Can we do much better? Is there another streaming algorithm that has much less than log n bits of space? In fact, this is the reason another reason we optimize our algorithm, because we wanted a result that's pretty tight. So the theorem is going to be that every streaming algorithm for L needs at least log n minus 1 bits of space. Up to these 2 bits difference, we know exactly the complexity in terms of memory of streaming algorithms for this problem. This is a pretty strong statement. Usually we don't know things to this level of accuracy. And how can we do that? I mean, we just encountered streaming algorithms. For DFAs, it took us quite a few videos to start talking about impossibility results. How can we so quickly do things for streaming algorithms? Well, because we are going to use things that we've already built for DFAs for streaming. So what we're going to use is the mile-narrowed theorem and the connections between DFA and streaming. The mile-narrowed theorem on its own doesn't apply to streaming algorithms. It applies to DFAs. But the connection between DFAs and streaming will let us use the mile-narrowed on streaming algorithms. And I want to say it already here, and I'll repeat it when we finish the proof, that something interesting is going on here. We are using a reduction of kind of between DFAs and streaming, but we're using it kind of in the wrong way. We're not using it algorithmically to solve something. We're using it to show that something is impossible. Well, let's discuss it a little bit later. We'll see examples of that all over this course. So that's the theorem. The theorem is that you need at least log n minus 1 bits of space. And the proof idea is to would consider, for simplicity, n that is even. Things would not change much otherwise. And what we're going to show is a set Sn of strings that are of length n over 2. And we'll have quite a few of these strings. We'll have n over 2 plus 1 strings. And what we'll have is that each pair in Sn is distinguishable in Ln. So this language, Ln, is going to distinguish every two strings. This means that even if you only care about strings of length at most n or exactly n, when you come up with a DFA or a streaming algorithm, when you remember each one of these strings, when you read each one of these strings, you need to remember it. You cannot confuse any two of these strings because that can lead you to a mistake. So the Mile-Narrow theorem is going to imply that every DFA recognizing LN or any other language that agrees with L on n-bit strings need at least n over 2 plus 1 states. And this will mean that every streaming algorithm for L needs at least log n minus 1 bits of memory on strings of length n. Because otherwise we can build a streaming algorithm, a DFA from the streaming algorithm, because we have a reduction. So, so let me continue emphasizing the point I mentioned about reductions. So usually, let's consider the story from one of the first videos. They talked about the mathematician that has to clean the house and therefore needs to fill the bucket. And there are two problems, one when the bucket has a hole in it, and one when the bucket doesn't have a hole in it. And there is a reduction. You make a hole in the bucket, and then you reduce it to this other problem that you already know how to solve, and therefore you solve it. This is usually how we look at reductions in an algorithmic perspective. We reduce one problem to the other, and since we know how to solve the other problem, we're going to solve it, which will imply a solution for the problem we care about. But in this class, we mostly are going to use it in the wrong direction, or in the direction that is more common in complexity theory, for impossibilities. If you have two problems, and you know that there is a reduction from this problem to this problem, but you know also that this problem is difficult, then now you know that this problem is difficult. Because if it wasn't difficult, you could have reduced this to this and solve it, but you know that you cannot solve it. So in the algorithmic sense, you know that if there is a reduction from here to here, and this is solvable, then this is also solvable. The flip coin is that if this is not solvable, then this is also not solvable. And that's what we're going to do here. Let's go back to what we're trying to prove. So what we're trying to prove is that there is this distinguishing set Sn with n over 2 plus 1 strings, such that every two strings are distinguishable in Ln. So this is the picture. We're going to define Sn. And if we partition all the strings into their equivalent classes under Ln, each one of the strings in Sn will be in a different equivalent class, meaning that the number of equivalent classes in Ln, and more generally in L, is going to be at least n over 2 plus 1. So this means that that the number of equivalent classes is going to be n over 2 plus 1, and this means that the DFA will need this many states. So the strings in Sn are going to be of length n over 2. And so the continuations we will care about will also be of length n over 2. And since all this language cares about is number of ones and zeros, then if we want to look at strings that are distinguishable to this language, we need to look at strings that have different number of zeros and ones. Every substring that have the same number of zeros and ones will be indistinguishable. So specifically, the strings are going to have the ith string, where I goes from 0 to n over 2, is going to have I ones, and n over 2 minus I zeros. So let's have two of these strings, x and y, one with k ones and one with j ones. where k is larger than j. What would distinguish these two strings? Well, it's not really very surprising. We'll assume that k is larger than j without loss of generality. It's not hard to see a way to make the number of ones in x exceed the number of zeros, but in y doesn't exceed the number of zeros. So the string that is going to distinguish is going to have k minus 1 zeros and n over 2 minus k minus 1 ones. And we claim that it distinguishes x and y. So let's see. xz has n over 2 minus 1 zeros, so it has more ones than zeros. We started with more ones than in y, and we crossed the threshold. We have n over 2 plus 1 ones. In y, we have less zeros, so this would not allow us to cross the threshold. So yz now has n over 2 plus k minus j minus 1 zeros, and n over 2 minus k minus j minus 1 ones. And the calculation is that k minus j minus 1 is at least 0, so yz is not in ln. It doesn't have more ones than zeros. So the string z distinguishes x and y, and they are distinguishable for ln, and that's true for every two strings in Sn, and this completes our proof. So very quickly, using methods we already had in the past, we can apply them here and show something pretty strong on the streaming algorithm. And to complete the proof, all pairs of strings in Sn are distinguishable in ln, so are at least Sn equivalent classes in ln, and also in general in L. And so by the mile-narrowed theorem, all DFAs recognizing ln need at least Sn states. And every streaming algorithm for L requires at least log of this number, log of the size of Sn bits of space. And since the size of Sn is n over 2 plus 1, we are done. So that completes the proof. So this was one problem. We don't want to have you think that that's the only thing that we care about in streaming algorithms. So let's get a little bit more interesting, a few more examples that are a little bit more interesting. And here it's going to be finding frequent items. So a streaming algorithm for recognizing L, when the stream is composed of ones and zeros, essentially ask if 1 occurs more frequently than 0. But what if the alphabet is more than just ones and zeros? So there could be many different symbols, and we may want to know which one is more frequent. So as an example, consider various search phrases that are used throughout the day. So search phrases can be pretty large. And we may ask which search phrases appeared a lot of times, which were the frequent search phrases, and this is important for various reasons. We care to see trends and also to prepare our search engine for the next day. So we can ask what are the top 10 symbols, or we can ask something a little bit different. And this is the problem we're going to look at: frequent items. Given k and a string x, which is x1 up to xn of symbols, output the set of symbols that occur at least or more than n over k times in x. So we care about all the strings that appear many times. the symbols that appear many times. How many symbols could S contain? Well, S can contain at most K symbols, because if there are more than K symbols that appear more than n over K times, then the number of occurrences altogether is more than n, but the length of the sequence is n. So this is kind of the top K items, but not exactly, because sometimes perhaps there is nothing that appeared a lot of times. For example, everything appeared once, or perhaps some appeared once, some appeared twice, and that's not interesting enough. So whoever appeared twice is not very frequent. In any case, this is the problem we're going to look at. And we're going to give an algorithm with two passes. Again, the two-path model is a little bit less interesting than the single pass, but it will allow me to show you something non-trivial already in this class, algorithmically. So I've shown you some impossibility, and I'll show you another impossibility later. And I also want to show you something non-trivial in terms of algorithms. And for this class, it will be easier for me to do a two-pass. For this problem, there are also interesting single-pass algorithms. So this one, we're going to use order k times log sigma, the number of symbols, plus log n space. And is it good? Is it bad? Is it a lot of space, a little space? I claim that this is pretty little, because first, let's look at k times log sigma. This can be the length of our output, right? We said that there could be k symbols that appeared that frequently. Describing each one of them would require log sigma bits. So even if we just want to maintain the output at every given point, that's what we need. In addition, we're also going to use k log n, which we could think about it as maintaining k counters for these k potentially frequent symbols. Of course, it's completely unclear how to use this few memory, because we don't know who are going to be the frequent items. So we cannot just count them. We see lots of symbols, and we don't know which ones are going to be the more frequent. So it's pretty impressive, this number. And here is the algorithm. It's a little bit subtle, and try to stay with me. And you can rewind me, and there is going to be notes about it. So initialize a set T, where every element in T is a pair. It is a symbol and a counter. Essentially, ideally, this set T would contain all the symbols we've seen so far and how many times we've seen them. We cannot do that, but that's kind of the ideal. Originally, this is empty. And now, every time we read a symbol, we're going to do the following. If this symbol already appears in T, then we already know some counter for it, and we're going to increment it. So if sigma m already appears, we're going to remove sigma m and insert instead sigma m plus 1. So you can think about it as incrementing the counter that is associated with sigma. Else, if the list is not too large, if it has less than k minus 1 elements, then we're going to just add a new element to T, which is sigma and 1, because so far we know that we've seen sigma once. This is a reasonable counter to see. And that's great. So far, if we could continue this way, then we'll have exact counts for all the symbols, and we'll know everything we want to know at the end. But as you can expect, it could be that we see a symbol that didn't appear, and so sigma didn't appear, and the list is already full. It has k minus 1 elements. We don't want to increase it beyond that. So what can we do? We cannot increase the list, and we cannot add sigma into the list. So instead of adding sigma into the list, we're going to take every other element in the list, sigma prime that appears with m prime, and we're going to decrease their counters. So for every such sigma prime m prime, we're going to remove sigma prime m prime and introduce instead sigma prime m prime minus 1. And if in this process m prime now gets to be 0, then we are just going to remove this element altogether. So before we did it, no element was 0, no index, no counter was 0, but now we decreased them by 1. Perhaps one of them was already 1 when we decreased it 0, and we don't need to hold 0 elements in our list. Okay. So this is counterintuitive, or at least unclear. What are we doing here? But let's see what we can get out of it. We can have the claim that T contains all sigmas, at the end, all sigmas that occur more than n over k times in X. That's interesting. Let me give you a hint about that. And we can discuss it further when we meet. And you can also look at the notes. So let's think about this algorithm a little bit differently. Instead of having a list of size t, of size at most k minus 1, imagine that the list contains all the possible symbols. You have a list of all the symbols in the world, or all the symbols that we'll ever see. And each one of them has some counter to them. But what T is going to be holding at every given point is at most k minus 1 of them. And in fact, it's only going to hold all the ones where the counter is non-zero. So, so we're going to maintain the case where there are at most k minus 1 elements with the non-zero counter. But what do we do? At every given point, we see a symbol. We're first going to increase its counter by 1. Now, if by now we actually have too many, if this was the kth, if this made it the kth symbol with the counter that's larger than 1, we're going to decrease all the symbols with positive counters by 1. And now this element specifically is going to be thrown out in a sense. It's going to have a counter that's 0, so we are maintaining the idea that there are not going to be too many symbols with counters that are strictly positive. This is the same algorithm, but in fact, in our algorithm, we just don't remember all the symbols with a 0 counter. But it does the same thing. So now let's see what happens. We are going to increase counters n times. Whenever we see another element, we're going to increase it. We're going to increase one counter once. So the number of increases of counters is n. What happens when we decrease counters? When we decrease a counter, we don't decrease it for one element. We decrease it for all the ones with positive counters. And the number of positive counters has to be, in this case, k, because otherwise we don't need to decrease. Otherwise, we have enough room in T. So whenever we decrease a counter, we decrease it for k symbols. And whenever we increase it once. So we're going to increase counters n times, and we're going to decrease counters every time with k symbols. And we're only decreasing it to 0. We're never decreasing 0 counters. So this means, and it's easy to argue, that you can only do it n over k times. right? You cannot decrease more counters than you increased, right? You're increasing it n times. Each time you decrease k. You can do it at most n minus k times. So now let's concentrate on a particular symbol. This symbol is going to be increased its number of occurrences and going to be decreased at most n over k times. It means that when the algorithm ends, the counter that is associated with this symbol has at least the count of number of occurrences minus n over k. And if this number of occurrences is larger than n over k, then it will have a positive counter, and in particular, it's going to be in the list T. I hope this wasn't too confusing. If you rewind me and freeze me, perhaps you can you can recover it, and we can also discuss it when we meet. But given that that's what happened, now we can solve everything in a second pass. Because what we know now is that T after the first pass contains all the possible suspects to have enough occurrences. We have elements in T that perhaps didn't appear enough times, but we don't have any element that appeared enough times and is not in the list. So now let's go over the stream again. And now let's count all the occurrences, but only for the k-1 elements in the list. We have enough memory to do that because we are only concentrating on k-1 elements, symbols. And for each one of them, at the end, we're going to have exact count, and we know if it's above n over k or below it. So at the end, we're going to know exactly which are the elements that appeared at least n over k times, more than n over k times. So that's the algorithm. It's one non-trivial algorithm, and it's a beautiful algorithmic area. If you continue with theory, then this is definitely an area to look at. Right, so we are outputting all the sigmas that occur more than n over k times. So let's look at yet another problem. This is going to be our last problem. And this, so we've seen an interesting impossibility, interesting lower bound. We've seen an interesting algorithm. And now with this problem, we're going to see both an interesting impossibility and an interesting algorithm. And you'll see soon why, how. So this is the distinct element problem. We have a stream of elements. So the stream is X, and it contains elements from the set 0, 1, up to 2 to the k. So it's in 0, 1 to 2 to the k star. And we'll look at the setup of parameters where 2 to the k is larger than the length of the stream squared. So let's think again about our web page or a link, and we ask how many times it was clicked. But in fact, we want to see how many times it was clicked by distinct individuals, or how many distinct individuals visited a site. So the name of each individual is pretty long, and is much longer than the number of individuals that have visited the site. So this is the input, and the output is the number of distinct elements that appeared in X. So we have this stream X with very long names, and we ask how many distinct elements appeared in X. And there is a streaming algorithm for distinct elements that uses order kn space. How would we do that? Well, we're going to do it trivially because every element in X can be represented by by k bits. These are elements from 0 to k, to 2 to the k. And you need log of that to represent an element. And the length of the sequence is n. So you can describe the entire sequence in memory kn. So this is the trivial algorithm. You can always memorize your stream and then do whatever calculation at the end. This calculation is not very difficult once you have the entire stream. That's kind of trivial. Can we do better? Well, it turns out that you cannot do much better. Every streaming algorithm for DE requires omega kn space. So this is a good opportunity to refresh your knowledge about asymptotic notation, and I'll release a video about that. But essentially, big omega says that you need at least kn bits of memory up to a constant. So perhaps half kn bits of memory, 1/10 kn, but up to a constant, you cannot do much better than the trivial algorithm. This is, this is pretty horrible, but let's prove it. And then once we prove it, we'll ask what else can we do. So this is the symbols that we have. And we're essentially going to reprove a variant of the mile-narrowed. We are not going to use the mile-narrowed directly for this problem, just because originally we defined it for problems that are for languages. So we define this notion of distinguishability for languages. And this is not a language. This is a problem that has output that may not be 0 and 1. But essentially, this is going to be exactly applying the mile-narrowed or a variant of the mile-narrowed to this problem of distinct elements. So here is the definition. For every two strings, x and y, they are DE distinguishable if there exists some z, such that xz and yz contain different number of distinct elements. So this means that if you go over the stream, and perhaps it was, you saw x, perhaps you saw y, you need to memorize which you saw, which one of those you saw. You need to distinguish that, because if you don't know, if you reach the same state, then z will make you make an error on one of them. So lemma, let S be such that every pair in S is DE distinguishable. Then every streaming algorithm for DE needs at least log of S bits of space. And the proof is just like we had in the mile-narrowed theorem. We have the pigeonhole principle. If the algorithm uses less than log of S bits, then there are distinct X and Y in S that would lead A to the same memory state. Just there are not enough memory states for A to distinguish all of these strings in S. But X and Y, if they're in S, they are distinguishable, and they are distinguishable by Z. And therefore, the algorithm is going to make mistake either on XZ or on YZ, because reading X and Y leads to the same memory state. And now reading Z will make you output the same thing, the same number of distinct elements, but it's not going to be correct for both of them because they have different number of distinct elements. This is kind of a variant of mile-narrowed. And the other lemma that we need is that there exists a DE distinguishable set S of size that is large. It is of size 2 to the omega kn. And now taking the other lemma, the two lemmas together, we know that every streaming algorithm needs log of 2 to the omega kn bits of memory, which is omega kn bits of memory. And so what is this set S? the set S will contain a string xt for every appropriate subset of symbols T. T is a subset of sigma of size n over 2. And we concatenate all of the elements in T, all the symbols in T, and we get the sequence xt of length n over 2 composed of all the elements in T. And what we want to argue is that for distinct sets T and T prime, xt and xt prime are distinguishable. What would distinguish them? Well, xt in particular is going to distinguish xt and xt prime because xt contains exactly n over 2 distinct elements. By repeating xt twice, we didn't increase the number of distinct elements, we just repeated all these elements. And xt had n over 2 elements, so xt has again n over 2 elements. But when we look at xt prime xt, we have more than n over 2 distinct elements. We have the n over 2 distinct elements of xt prime, but but t and t prime are not the same, so there is some element in t which is not in t prime. And with this element, we're going to have at least n over 2 plus 1 distinct elements. So xt and xt prime are distinguishable, and there are many of them. And the total number of subset is at least is 2 to the omega kn, where 2 to the k is larger than n squared. So this is where we use this assumption. So this is a horrible state of affairs. Why is it such a horrible state of affairs? It is because this is a very basic algorithmic question. We want to solve it, we need to solve it. And if we cannot do anything other than the trivial thing for something which is pretty basic and simple, then this is a horrible algorithmic field that cannot do even the most basic things that's needed in a non-trivial way. And the trivial way is just not practical. We said that we're talking about streams that are very, very long, so it is completely impractical to store these entire streams. But fortunately, we have randomization to our help. So randomness is another resource of computation. At times, randomized algorithms, in particular settings, randomized algorithms can be better than deterministic algorithms. It's an entire area that's very interesting, and I'll be happy to discuss it offline. But here we're going to see one example, our first example of when randomization helps. So we have our distinct element problem, and it turns out that there is a randomized streaming algorithm that is not perfect. It doesn't give you exactly the number of distinct elements, but it approximates it up to a very small error, up to 0.1% error, which is impossible with deterministic algorithms, using extremely little space, k plus log n. So instead of using k times n, we're using k plus log n. Essentially, the memory that can be used to store a few symbols and a few indices into the stream x. So a symbol is of length k, and a few elements, indices in 1 to n. And I'll give you a hint. It's not very important. I don't expect you to understand this algorithm, but I just don't want to keep you in suspense. I'll give you kind of a few hints about how these algorithms work. It's not complicated, and we're going to see another randomized algorithm in the next video. So imagine, right, we talked about individuals coming to a site, and we're asking how many distinct individuals there are. And the names of individuals go between 0 and 2 to the k. Imagine that all the individuals that visit get random names. So, so the first individual to arrive is I, where I is uniformly chosen between 0 and 2 to the k. And so with the second one, the third one, if the fourth one is one we already saw, then it gets the same name as before. But for any new individual, it gets a random name. In that case, we can do something interesting. We can approximate how many distinct elements we got, for example, by looking at the minimal name that appeared. Right? It's easy to maintain the minimal name, because whenever a new symbol arises, you ask, is it larger or smaller than the minimum so far? And once we end, we are ending with the minimal symbol. Now, why would the minimal symbol give us an indication on how many symbols we saw? So imagine that the names are uniform between 0 and 5,000. And furthermore, imagine that the minimal element that you saw is 50. So now, if you assume that elements were essentially spread out of equal lengths, and if they are uniform, they will most of the time be mostly spread out with equal distances, then you expect the minimal value to be 50 if you've seen roughly 100 individuals, assuming that 5,000 over 50 is 100. I think so. But if, on the other hand, you saw 500, it's the minimal value, then probably you saw around 10 distinct individuals, and then the minimum will be around 500. So this gives you some indication. But we have several problems to solve. First, that this indication is only correct in expectation. And the second one that seems more problematic is that individuals that arrive are not necessarily uniform. Perhaps the individuals that arrive are 0, 1, 2, 3, up to the number of distinct elements. Your algorithm will fail. So now we'll make another crazy assumption. And this assumption that is that somewhere in the world, there is a random permutation H that is available for you over the names of individuals. So H permutes 0 to 2 to the k. So what can we do now? Now, instead of looking for the minimal individual that arrived, the individual with the minimal name that arrived, you can look at the individual with the minimal permuted name that arrived. So if you see Omer, then you don't ask if Omer is the minimal individual, but you look at H of Omer. And you ask if H of Omer is the minimal value that you've seen. And then the algorithm would work just as if you have random names. It's not your original name, but it's the name the algorithm gave you by age is random. So the minimal age of an element is going to give you an indication of the size. Now we can also solve the problem that this indication is only correct in expectation. And in fact, instead of doing it with one permutation H, we can do it with several permutation H's. And the number of permutations that we want would depend on this 0.1% error. And for each permutation H, we'll get some estimate for the number of elements that we saw, the number of distinct elements. And if we take something like the median or some other estimate, we can do pretty well and get something that's a pretty good approximation. So the only problem that remains is that we don't have random permutations kind of floating in the world. You need some concrete permutations that will be random enough. And this is an entirely different area of research called de-randomization or pseudo-randomness. So instead of looking at random permutations H, we can define pseudo-random permutation H. And these have short descriptions, and the algorithm first will choose a few of those and store them and run the algorithm. And that will be okay because these permutations, these pseudo-random permutations, are going to have very short description. So don't worry if you didn't catch this algorithm exactly or even vaguely. I just didn't want to make such a strong statement without backing it up at all. But if you didn't follow me, feel free to ignore. So let's finish with kind of some thoughts. First, DFAs are very, very relevant, and these are the modern day incarnation of DFAs. And the tools that we developed for DFAs, in fact, are very relevant for streaming. And the other thing that we saw, and we saw it in the first time, but not the last time, is that randomness can be a useful resource of computation. And with that, we'll finish. Thank you.